Okay, so welcome everybody, lecture 9. So today we start basically with the course proper. We discuss our first computational model, the one that we will discuss at some length, and that's quantum computation with magic states. Okay, so there's two items to discuss. We first have to discuss what the model is, how it deviates from the circuit model. It will be a minor deviation from the circuit model, and what the advantage is. And then I will also briefly mention why we are looking at this model in this course. It's more for theoretical reason than for practical advantage, but we discuss this next time, and today it's mostly about the practical thing of it. Okay, so quantum computation with magic states. Okay, some reading. The basic new element is state injection, and you can read about that in the Nielsen and Schwang. And then, what makes this protocol, this computational scheme, interesting for fault-tolerant quantum computation is this procedure of magic state distillation. So we will talk about that today, but not at very great depth. And so you can read it up there in this paper. Okay, so what is this computational scheme? So it's like classical computation with a reduced instruction set. So you have fewer gates than you previously had. So you have CNOT gate, a Hadamard gate, basically all Clifford gates. And you have Pauli measurements, and that is it in terms of gates. And so now the Gottesman-Nil theorem tells you that this is not enough for computation if you were also talking about stabilizer states only, but that's not what we do. So we add other states, and in this way we regain universality. So we are compensating the missing T gate by certain states that we permit. And why this is a good thing to do, that's what we will talk about today. And I guess you'll have a little bit to do towards that also. Yeah, and then the question is, and that's the question for next time, apparently computational power is shifted from the gates to the states because the gates by themselves are all Clifford and don't do very much. Yeah, and so you may ask, now that somehow the power of computation must reside in these magic states, and what property do they have that makes them computationally useful? And we will find that this has something to do with Wigner functions, namely there can be speed up only if their Wigner function is negative. Who is familiar with the concept of a Wigner function? It's probably a thing that you learn in quantum optics. Anybody heard about the Wigner function before? Aha, oh good. Well, okay, so then you will learn it here for the first time, but the Wigner function is a concept from quantum optics. It's not something that quantum information people have invented. It has existed for 100 years, almost. Let's say 90. That's what we will discuss next time. So there's a theorem about that for various scenarios. And it says that quantum computation with magic states can have a quantum speedup only if this property, this Wigner function of the initial state, is negative or takes on negative values. It's a function over phase space, and only if it dips below 0, then you can possibly have a speed up. This is the reason why we are talking about this model, and that's going to happen next time. Okay, so now, let's talk about this injection circuit, and I thought maybe I let you do it. Okay, so maybe you can quickly calculate that for me. And you can move closer together if you want. You can form groups. Or you're just in time for the exercise come in. So if you want, you can do this, for the first exercise, I should say. So you can do this alone, but you can also do it in groups if you want. Yeah, so the question is, what is the effect of this circuit? So let's see what's going on here. We have two incoming state, and so that state is a fixed state. So this is kind of the magic state that we are putting into the system, and it is defined like this. So it's an equal weighted superposition basically of 0 and 1, and then it has a relative phase, and the value of the phase matters, and that's what's characterizing the state. And so you know what that phase is, and you put in that thing. And psi is an unknown quantum state. And so quantum, a qubit of your quantum register, basically. And so you entangle these two qubits and then measure one of them down here. So the observable is the Pauli phase flip operator Z. And for now, we assume that the outcome is +1, positive eigenvalue, projection, yeah. And so the question is, what comes out? Yeah? So how does what comes out depend on the state that you put in? And how does it depend on that phase, phi? Okay, so that is your question for now. Yeah, so maybe you have 5 minutes or so. Okay. So the notation wasn't clear. So if the notation isn't clear, I mean, you're wasting lots of time. So please ask question. So again, this means the Pauli observable Z is measured and the outcome is +1. So that's what this notation means. If you have other questions, please ask. You can ask me or you can ask your neighbor.
This measured on the second system.
Yeah, on the lower system. Yeah, exactly where it is shown.
The comma could do a statement for one.
Yeah, it could be. I mean, you can, yeah, I see now. I mean, you could call your lower qubit 1. Yeah, so it is Z, comma, plus. Yeah, measured observable Pauli Z, eigenvalue +1. Okay, so I got the question. The projector for measuring Z with eigenvalue plus. This is, the way we wrote it in the lecture, is I plus Z divided by 2. And it is also this. Okay, and I just got the question why this is so. And for figuring this out, I mean, we write both the identity and Z. We just write it out in terms of rank 1 projectors. So it's positive eigenvalue +1 for the 0 state and eigenvalue -1 for the 1 state. And so for the identity, it just has eigenvalue +1 for both. Okay? And so now you add these two things up and divide by 2. When you add them up, this survives, this cancels, so you get 2 times this projector, you divide by 2, here you go. So not, yeah? Yeah, so now, from now on, you don't need to calculate it. Good, I think we need to continue, but since there were difficulties with this problem, I would like one of you to show it, to show your calculation. I mean, you can do the whole thing, but I just didn't see the phi in the unitary. That was confusing me.
So what I started with is this is and this data is defined as the general state.
Okay.
And so this state and this state can be combined together. So it gives which is so it, then then we perform the synod gate. So it acts on the state that have the first qubit equal to 1 to reflect the bit of the second qubit. So if and we said that at the end of the second qubit, we measure C and we get the eigenvalue of +1. So it means that the final state of the second qubit must be 0. This one. So I just select the second, the state that have the second qubit equal to 0. So this term comes. And what I get is this. Actually, this thing should be A and B. Yeah.
Mm-hmm.
This should be. So the final state is this one. It means that we can transfer the prefactor A and B to the upper state.
Exactly. So you see, second qubit is 0 in both cases. So we have a tensor product. Maybe you can write it out, what the tensor product is. Thank you very much. This is good. So, fantastic. And maybe last thing. Tell me, how does this state differ from the state that went in?
It's modified by the prefactor of the second qubit. The second state.
The second state. You mean like here? This prefactor is modified. That's what you're saying? Or what are you saying?
I'm saying this one. Prefactor.
Mm-hmm. But were they not what you put in? The incoming state?
I put in this one, and it's transferred to this one.
Oh yeah, okay, so look, the support has changed, yes? And if you compare what you put in and what you got out, what is the difference? The phase.
Yeah.
Okay, so that's, thank you very much. Good, so you are released for now. Thanks a lot. So this phase here is the reason why we did all this complicated song and dance for this phase. And so there's another way to write it to make a little bit clearer what happened. So this is a unitary U of phi applied to the state that we put in. So recall the state we put in was this. Okay, and then so we have the trailing 0. Okay, and that unitary that I have defined here, this unitary is there's a rotation about the z-axis with angle phi. Okay. Yeah, so in matrix form, this is minus e to the minus I phi over 2, 0, 0, e to the I phi over 2. And so this is up to global phase. So this is e to the minus I phi over 2, identity e to the I phi. Okay, so now you recognize it. So this unitary, I mean, global phase, don't worry about that. This has no physical consequence. So for the state 0, yeah, nothing happens. And for the state 1, the phase is acquired. This is precisely the phase that you see here. Okay, so that is this was the purpose of the exercise. And so we have to talk a little bit about the significance of this. Okay, we have to talk about the significance of this. So this is e to the minus I phi over 2 z times incoming state, and that we call uz of phi. It's a unitary. Okay, so that's what we did. So the upshot of this so far is that we have replaced the unitary that we could have done otherwise by a state, or we have found a way to convert a state of a certain form into a unitary. And for the moment, it's just kind of like an awfully complicated nonsense, but it will become very important. And the purpose of this lecture is to show you that this is a good thing to do. And that will take us a couple of steps. Okay, we have some time to catch up, and so I cannot let you go into the break yet. So what we are now going to do, and now you have all seen how to do it, now we're going to do the same thing, but with a minus sign. Yeah? So measurement has probabilistic outcomes in quantum mechanics, so we have to talk about what happens if we get the opposite sign. And that will result in not in a catastrophe, but in a medium complication. Okay, so this is actually something that we will have to address. Okay, so go for it. So before the break, please now, remembering how this was done, do it for the other outcome. Yeah, so now the projection is onto the opposite state, on state 1. And again, so the end result you should really write again, outgoing state is incoming state and a unitary applied to it. So you should identify that unitary. Okay, let's say we will have to catch some time. Let me fill that in here. So we have e to the plus I phi over 2 z times x. Actually, it's the wrong order. Apologize for that. We have okay, good. So that is what we are getting now. So we have two changes. We have the sign flipped, and we have a Pauli flip in addition. Okay, so let's talk about the significance of that after the break. So that is our result for now. Okay, so yeah, so let's sum up. Is this good or bad? This is really not so good. So the x here happening after the rotation, so this is not so dramatic. We know when it is there, it's triggered by the measurement outcome, so we can just undo it. So that would be fine. But the sign is off compared to the previous case. And so we probabilistically do the desired rotation, and in the opposite case, we do the inverse of the rotation. Yeah? So we cannot choose. We must live with the outcome we get, and then either we do it correctly or we do it wrongly, and we know what happened, but yeah, so the question is how much that helps us. So this is not a deterministic gate action. So this is not good enough. We need to work a little harder than this. Okay, and so now we observe the following. So this is the gate we wanted. In the second case, this is the gate we got. And we can get from what we've got to where we wanted by just compensating with a rotation that has twice the rotation angle. Okay, we know we go from phi to 2 phi, rotation angle. And so now we do this for one particular angle. So for the angle was free to choose, but now we are looking for our universal gate set. So now we are making a specific choice for this angle. And the angle is pi over 4. So this gives us, so this gives us here the t gate, and here it gives us the so-called s gate. This is t squared. That's a Clifford gate. So that's the important thing. The correction that we can do in the second case to go from where we ended up to where we wanted to go, this correction is a Clifford operation. You know, and Clifford is simple. So Clifford is something that we can do easily in our magic state computation model. So here is now the full magic state distillation circuit. So first let me say what it does. So it uses up this ancilla state T, which is just this. It takes any input state into the unitary T, so this rotation about the z-axis, applied to that initial state. Okay, and so how does it operate? Well, we have the C0 that you invoked in your calculations, we have the Z measurements, and then depending on what the outcome is, a controlled operation X first, then S is applied. So the X cancels the X that you saw, and then the S is to cause this effect. So this happens only when the measured eigenvalue is -1, and if it's not, then just no correction operation. So this combines the two cases we had, and well, it does the T gate now with stabilizer operation, Clifford unitaries, and Pauli measurements. So you consume the state and you get the gate. Okay, it looks like a fairly complicated procedure to get such a gate, but we will see that it is a good thing to do. Let's step a little bit away from the issue and see what caused this difficulty here. So if we step a bit away, what we see is, okay, so this whole complication was caused by the fact that measurement outcomes are probabilistic, and we have to live with what we get. We cannot choose the measurement outcome. So if we got the positive outcome in our procedure, we are getting the gate we wanted right away. But if we get the negative outcome, then we get the inverse of what we wanted, and then a Pauli correction. The Pauli correction was easy to deal with, but the wrong sign here, the inverse, was a little bit harder to deal with. But that is, the randomness of quantum measurement is the reason for the complication here. Oh, so there's something to draw. And so there is a general structure that's in the background here, and it's called the Clifford hierarchy. And I want to talk, I just want to introduce the term of Clifford hierarchy because it comes up in these discussions. Okay, so let's modify these expressions a little bit. So the first thing I'll do is I exchange the order. X and Z commute, so that flips the sign actually. So, but now there is, so so this gives me the sign back that I wanted, but I haven't really solved the problem here because now I have this X error sitting there waiting to be corrected. Okay, so it's just a manipulation by itself, doesn't do much for me. Okay, so now we are making it a little bit more complicated even by multiplying on here this identity. Putting some brackets. Okay, and so now this erroneous gate, so now how have we written that now? So this was the intended gate and this is a correction. Okay, and so sometimes we are lucky and the correction is easier to make than the intended gate. So suppose this is what you wanted, but you got the wrong outcome, and so you got this, which is what you wanted times a correction. So you want to undo the correction, and sometimes undoing the correction is a simpler thing than doing that in the first place. Okay, and you will have a magic state that undoes this correction. And so you will be invoking successively simpler magic states, and that is related to the structure that's called the Clifford hierarchy. And so to motivate the notion of the Clifford hierarchy, so let's look what the correction is like. Yeah? So we have a Pauli operator conjugated by the gate we cared about. So that's it. Okay, so now comes the Clifford hierarchy. So the Clifford hierarchy is a set of gates. So there's various levels in the hierarchy, begins very simple, gets progressively more complicated, and these levels are recursively defined. The first level is the n-qubit Pauli group. So now let's try to parse it. So the second level here in the hierarchy is what maps Pauli operators under conjugation to the previous level, which was level 1. So it maps Paulis to Paulis. We know what that is. That is the Cliffords. Yeah? So second level of this hierarchy is the Clifford group. So that's not good enough for universal quantum computation. We need to get at least one level higher. And so this is the third level. And so we need to look at the gates that, upon conjugating Paulis, will get us to the Cliffords. So this is the third level of the hierarchy, and the stuff that's in that set suffices for universality. Okay, and so we can show that gates at finite levels of the Clifford hierarchy can be executed through magic state injection with certainty at bounded cost. So this is basically what we've seen. So this is what you want to do. For example, we have it seen here for the special angle of phi equals pi over 4. So what you want to do is the T gate. Sometimes after the measurement you don't have it yet, and you need to do a correction, and that correction is Clifford. So this is how you'll get to the third level of the hierarchy. So I just wanted to point that out. So if you want to do fault tolerance professionally, then you'll hear Clifford hierarchy a lot. Okay, but for us, it's just a side remark. Good. Okay, so basically the hierarchy, why does the structure come up? And the reason it comes up is that either you view it, you have the wrong sign, probabilistically in your unitary, or you have the Pauli correction and the unitary in the wrong order. That is the reason why all this complication arises. Okay, and that shall suffice for the Clifford hierarchy. Good. So we have a bit of time and we need to speed up. So no more exercises for you. I had 2 more planned, but I guess I'll do them myself. This is a slide from a couple of lectures ago. So what we are very concerned with, so we have 2 computational models, A and B. So in this case, it will be the circuit model and model of quantum computation with state injection, which we know now. So by the way, what we've done is the universality proof. So we have shown that we can simulate the circuit model in the magic state model. That's what we've just shown. That's what you have shown with your 2 exercises. And the other direction is the trivial one, because all the gates you have available in the magic state model, you also have available in the circuit model. Okay, so we have these 2 models here, and they are computationally equivalent upon polynomial overheads. But now we want to know, how do their noisy versions compare? And so we already know this for the circuit model. The circuit model is fault tolerant. And it turns out our magic state model is also fault tolerant. So if the noise is not too strong, the computational power, the universal computational power, persists. Now, if you look a little bit more closely, what then happens, you find that this model actually does better than what it descended from, the circuit model. Quantum computation with magic states does better in terms of fault tolerance, and that is, somewhat better. Both models are fault tolerant, that's the main thing to say, but if you look a little bit more closely, you find that quantum computation with magic states does better. Okay, and I want to explain that to you why this is. So the upshot is, if you were to implement, as we know today, if you were to implement fault-tolerant quantum computation, you would go the magic state route. Okay, so what is there to look at? Before we get really into the weeds, there are 2 characteristics that characterize the performance of a scheme of fault-tolerant quantum computation. So the first and foremost number is the value of the error threshold. So there is this point, remember from last time, where error correction collapses, and that's the point of the threshold. You always want to be below. And so you want that value to be large. You want it so large that you can get to it with near future, let's say, technology. Yeah? You don't want this value to be 10 to the minus 50. You want it maybe 10 to the minus 2 or something like that. Okay, so that's the first number, the threshold value. And so then, second item after the threshold value is the cost of fault tolerance. You want to know, I have to run error correction, everything is going to get bigger. How much bigger is it going to get? What's the overhead? And the first thing that you will get to is that there is a scaling exponent. There will be certain scaling relations, and better scaling means lower exponent. So that exponent is what we are going to look at too. So we have a threshold value and we have a scaling exponent. And I want to show to you that both will be better for quantum computation with magic states than they are for the circuit model. So before we go to that, we have to calculate this both on the circuit model side and on the magic state side. Okay. So let's go back to the circuit model, and let's talk about the error threshold under super idealized assumptions of a transversal gate. So this is the idea. We are doing some unitary gate in a transversal fashion. Yeah? Transversal gate action we talked about last time, and then this transversal gate action will be preceded and followed by error correction, and let's assume, which is of course unrealistic, that these error corrections are perfect. We are just trying to simplify this situation as much as we can. And so then the question is, what is the error threshold? Good, I think we did that last time. We did it for memory and for transversal gate action. It is actually not that complicated. Okay, and so then there's the second question. Then, okay, so suppose we have the threshold, and then how does the cost scale with the remaining logical error? So we want to make this remaining logical error very small, and that will cost us something. How much? Okay, so these are the 2 questions we want to answer. Okay, and so that was the intended next exercise, but it looks like I'm going to do it myself. Due to time reasons, there's only 15 minutes remaining. Okay, so let's see specifics of our question here. So we have We are encoding 1 qubit for now. We use n physical qubits for that. And we're furthermore using a code that corrects 1 local error. So for 2 local errors, it's going to fail. Good. So that are the specifics of our setting. Yeah, and so, okay, so let's, so threshold is going to come first, and then we talk about the overhead. And so, yeah, so remember that picture. So what we are going to do is we will be looking at code concatenation. Yeah, so we remember that curve. Logical error at level L goes to logical error at level L plus 1, and PL plus 1 is for precisely this type of code we're looking at, where it corrects 1 local error. So this is some constant C times PL squared. I hope you remember this relation from last class when we talked about the error threshold of the Steen code. And so the constant C here is, in this case, n choose 2. Yeah? So the 2 local error kill us, and there's n choose 2 of those. Okay. And so now we're looking at the threshold of this thing. And so the threshold, okay, so we are solving for the point where PL plus 1 equals PL. And so that gives us the threshold probability is 1 over C. So this is 1 divided by n choose 2. So let's remember that. So for the Steen code, I mean, this is a really back of the envelope calculation. It's inaccurate in many ways, but just remember for the Steen code, n was 7, 7 choose 2 is 21. So we are talking about a 5% error threshold here. Okay, so that was the error threshold. Yeah, I hope some of you do remember it. Good. Okay, so now let's do a calculation that we didn't do last time. So there is this concatenation of coding. So for the Steen code, first level has 7 qubits, second level has 7 to the power of 2, 49, then 4 to the 3, and so on and so forth. So yeah, so we're going to talk about the overhead now. So the number of qubits as a function of the concatenation level is n to the L. N is the number of qubits in the code. L is the number of concatenation levels. Yeah, it's exponential in L. Okay, now next question is, what is the residual error of as a function of the concatenation level? Okay, and so we get this from our previous formula that we had here. So what I do this to see a little bit clearer what's going on, I take this formula and multiply it with C. So we have Cp goes to Cp squared. Yeah. Okay, and so now you see, now it is a simple relation. So now what we now find is that Cp at level L is, I mean, constant times residual error probability is Cp at level 1 to the power 2 to the n. Yeah? Cp goes into Cp squared, is squared again, so it goes to Cp to the 4th, and it's squared again, so it goes to Cp to the power 8, and so on and so forth. When you now look at this, so you had exponential scaling in L for the cost. You have double exponential scaling in the error suppression. Yeah, and so now you want to see how that trades off against one another. I mean, when you saw the exponential scaling in L, maybe you were concerned, but it is overwhelmed by this even faster scaling over here. And so now, final conclusion. I will spare you the calculation, but I will just write it down here. So the cost is proportional to log 1 over the target error. Yeah, so it's written like this because the error is supposed to be small. We want a positive quantity here. Raised to some power, and that power is log base 2 of n. So remember, n is the number of qubits in the code. So where does this power 2 here, I mean this base 2, come in the log? It comes from here, from that 2, and that 2 in turn comes from that 2. So it comes from the fact that you can correct one error, and for 2 errors the correction will fail. So that is where that 2 comes from. And so this is the scaling exponent of interest. Yeah? And now you see the following. Okay, I think I have the calculation here. The number of errors you can, down here, this is the number of errors you can correct plus 1. This, I mean, in other words, where the error correction fails for the first time. The more errors your code can correct, the better it is. The smaller this exponent will become. And also, this exponent will be the smaller, which is good, the smaller your code itself is. Good. So I want you to remember that. The more errors your code can correct, the better, also for the cost. And the smaller your code is, the better. Okay, so this is basically the calculation for the error correction side. So we have this exponent there. Now let's talk about the gate we care about. So this was so far for any code, basically that has a transversal gate, and for any gate. So we are now interested in the transversal T gate. So the T gate is the main discussion here in this model of quantum computation with magic state. To get the T gate, which is not Clifford, in a stabilizer code is a rather rare occasion. It's kind of funny that it appears at all. But it does happen. You get it for the 15-qubit Reed-Muller code. I alluded to that last time. Okay, so now we apply the calculation that we did to that code. The 15-qubit Reed-Muller code has 15 qubits, obviously, and it corrects one error. So the threshold is 1 over 15 choose 2. Yeah? So this is 1 over 15 times 7, which is approximately 1%. Yeah. You see we are down from what we had for the Steen code. Steen code had about 5%, now we are down to 1. So this is not good. So you wouldn't want to use the Reed-Muller code if you didn't have to. But the Steen code has no transversal T. So that's why we are using the Reed-Muller code to have a transversal T. Okay, so threshold went down. Also a scaling exponent doesn't look all that good. It's log 2 of 15, which is almost 4. So this is worse than you would have it for the Steen code. But again, you can't use Steen for the transversal T. So the fact that you need to do the T gate fault tolerantly, and not many codes do that for you, you get these numbers that don't look particularly good, like the 1% threshold and that scaling exponent. So you're forced to use unfavorable codes to retain universality. Okay, so that was it for the circuit side. And now we are asking, what about magic state injection? Does magic state injection help us with this? And it actually does. And so the question is, can you make the T state more robustly and more efficiently in a fault-tolerant fashion than the T gate? And the answer to that is yes. Okay, and that's the last thing that I want to squeeze into this lecture. Okay, so let's go for it. And so that's magic state distillation. And so I do not have the time to talk about the protocol in detail, but if you find the subject interesting, why don't you go right to the source? So this is this paper here by Sergei Bravy and Alexei Kitaev, published in Physical Review A in 2005. Okay, so just kind of broadly speaking, what's going on here? So how does the procedure operate? So it's a procedure that is made solely of Clifford operations, like error correction typically is. It takes 15 of these T states in, and they can be relatively noisy. So it takes them in, lots of noise on either one, cranks them through a Clifford circuit, and then we have syndrome measurement. Yeah? So there's 14 bits of syndrome that we obtain, and we discard the output whenever the syndrome is non-trivial. So we're just kind of dumping something when we don't think we like it. And note that this is not an option in a circuit. Yeah? So if you did your gate and got a syndrome that you didn't like, you cannot dump the state because it's the 10th millionth gate in the circuit and you have already invested that history of gates. However, the T state is just freshly made, and so you can dump it if you don't like the syndrome that you see. Okay, so this is the advantage that is really used here. We have a post-selection process. Okay, so we are selecting on trivial syndrome. And what one can then show is that out comes a much better T state, just one copy, than the noisy 15 that you put in. And so the point is, this post-selection, it detects all errors of weight 1 local errors. It also detects all 2 local errors. Where it begins to fail is with the 3 local errors. So sometimes you will be fooled into thinking there was no error when there in fact was one. But the point is that after post-selection, the non-detectable errors, they go now with error probability cubed. Previously, we had error probability squared. This power has now changed. We are talking about p cubed. So again, we have a recursion relation. But this time, it starts out as p cubed and not as p squared. So that's a much steeper, much slower start, and then going to get much steeper than p squared. And so as a consequence of this, the threshold changes. So the threshold used to be around 1%. The threshold is now at 14%. So with this, with this post-selection trick, we get a much better threshold value. I mean, it's not that this is going to be our final threshold, but the T gate will no longer be the weakest component. So that is what it really means. Okay, so that is in terms of threshold. I mean, we have improved the threshold significantly. Also, scaling exponent changes. So recall, this number down here in the log of our scaling exponent came from that scaling. That scaling is now pi cubed rather than pi squared, and consequently, the 2 changes into a 3, which brings down the scaling exponent. Yeah? So we are getting more robust, but we are also getting more efficient. Okay, so this is the upshot now. Magic state distillation does 2 things. It eliminates the T as the most error-prone component in your fault-tolerant circuitry, and also renders its implementation more efficient. Quantum computing with magic state is the way to go for fault tolerance. Yeah? Most efficient, most robust. Okay, so that's it for today. Yeah, next time, Wigner functions.